Welcome. We are looking at phase field modeling. We have looked at some materials thermodynamics, regular solution models, and we have looked at diffusion. We have looked at the classical diffusion equation. We have also done some analytical and numerical solution of the classical diffusion equation. And this lecture onwards, we are going to do the mathematics that is required to understand the derivation of the phase field equation, namely the Cahn-Hilliard equation, which is the first phase field equation in which we are interested in. So, to do that, we have to understand several concepts. One is tensors, the other one is some variational calculus. So, we will start with tensors. We will go back to the fixed first law that we defined and let us look at it a little bit more carefully. The fixed first law says that the flux is negative diffusivity times concentration gradient, and flux is basically a vector, and this mark on del here is to indicate that this del C is basically also a vector. Now, what do we mean by vectors? We know that vectors, right. So, both J and del C are basically vectors. Okay. So, what is the meaning of vector? Vector is a quantity with a magnitude and direction. Okay. So, vectors are quantities with magnitude and direction, and so when we say flux, it is not just sufficient to say how many atoms per unit area per second, but we also have to say in which direction. Okay. Similarly, when you say concentration gradient, it is not sufficient to say this much concentration across this distance, but we also have to say it is set up in which direction. Okay. So, this is the simplest definition of vectors that we know. We say that scalars or quantities with only magnitude, right. For example, the composition field is a scalar. Now, if we are very careful, then one has to distinguish the scalar composition, for example, from the diffusivity. Okay. Strictly speaking, D, which is the diffusivity, is a second rank tensor. Okay. So, now we want to understand what these tensors are. I mean, what is this second rank tensor, and in the tensor language we say that vectors are basically first rank tensors, okay, and scalars are basically zeroth rank tensors. Right. We want to understand this concept of tensors a little bit more carefully, but the way we have defined, like scalars are quantities with only magnitude and vectors are quantities with magnitude and direction, does not help us to generalize to second rank tensors. Okay. Quantities with only magnitude are scalars, quantities with magnitude and direction are vectors, which are first rank tensors. And so, what is a second rank tensor? Now, it is not very easy to generalize this concept to second rank tensors. So, what we are going to do is that we are going to define vectors a little bit more differently. Conceptually, it is the same. After all, vector concept is not going to change, but our description is going to change. And this description we are going to use so that it is easier for us to generalize to higher order tensors. Okay. So, the first sort of generalized description that we want to have, which helps us understand higher rank tensors better, is to actually look at what these vectors are, right. So, when I say the vector j is equal to minus d del c, I need to say what this vector is. So, suppose if I tell you, okay, let us say that this quantity has some direction, let us say that my flux is in that direction. Okay. Then how do we describe it? One is to say the magnitude and the direction, that direction is given with respect to, okay, let us take a reference axis, with respect to it, it is rotated by so much, right. And there is a much better way of describing that, and that is by first pegging a frame of reference. Okay. I am going to say that this is x, this is y, this is z. And then I am going to say that let us take the component of this flux tensor, flux vector, right, j is the flux. Let us take the component of j, so that is jz, and if you look at its components on x and y, so you have jx, you have jy, right. This projection here, so and that has x and y components. So, another way of representing actually these vectors is to say that j vector is nothing but jx, jy, jz. Okay. Sometimes it is also written in matrix notation, okay, which I prefer for reasons which you will understand a little bit better in a moment. That j is actually 3 components, and the 3 components are arranged as a matrix. It is a 3 row 1 column matrix, right. So, this is another description of the vector. It has the same information, because this j is some vector like that. So, I have split it into its components, and the components with respect to some reference frame is what makes this. Okay. Once I have, so j as a quantity, when I write like this, I am not talking about any frame of reference. But if suppose I can define a frame of reference, with respect to that frame of reference, then j can be written as a vector, as a column matrix, or as ordered numbers, right. So, a vector can also be represented like this. And when we represent it in this manner, so there is a more generalized vectorial notation, which says that instead of putting an arrow on top, I am going to write j of I, where I runs from x, y and z. Sometimes people also replace x, y, z by I equal to 1, 2, 3, in which case what they do is instead of x they say it is x1, instead of y they say it is x2, instead of z they say it is x3. So, the components are then known as j1, j2, j3. So, in a 3 dimensional space, if I have a vector, then the components of that vector resolved along the 3 reference directions that I have taken, they basically form a column matrix. This is another representation for the vector. So, now I am going to define a vector as a quantity which is represented with one index when you choose a particular frame of reference, right. So, I am going to say that scalars are quantities with no indices. So, that is why it is 0th rank tensor. Then I say vectors are quantities with one index, that is why they are first rank tensors. Then I can say, if I want now second rank tensors, I will say that those are quantities with 2 indices, right, and so on. So, if I go to nth rank tensor, then I say that those are quantities with n indices. Now, what is the advantage of defining vectors as quantities with one index? Because it automatically then generalizes the second rank tensor, third rank tensor, fourth rank tensor, etcetera, up to any nth rank tensor. Okay. Now, it is very important to notice that the index should not be confused with the range over which the index runs over, right. If I have a vector which is in 2-dimensional space, it still has one index, just that the index runs from 1 to 2 or x to y. If I have a vector which is living in 3-dimensional space, it still has only one index, but the index runs from 1 to 3. If I have a vector which is living in some 5-dimensional space or 4-dimensional space, sometimes in physics you might see 4-dimensional space vectors, 4 vectors. They live in a space which has 4 dimensions, right. Relativity, probably you have seen that it is x, y, z and it, right. The time dimension is also there. So, then it will have 4 components. Okay. I is still equal to 1. A vector in 4 dimensions still has only one index, but the index runs from 1 to 4 because the vector is now living in the 4-dimensional space. Okay. Similarly, if a vector which is a first rank tensor can have indices running from 1 to some m, where m is the dimension of the space in which this vector is living. Okay. The most important concept here is that we are assuming that these quantities like vectors and tensors are quantities which are physical, in that they have their own existence, that when we decide to refer to them with respect to a specific frame of reference, then we get the indices corresponding to that vector or corresponding to that quantity. Okay. So, the index is basically coming from our description, index is coming from our description or our way of describing the vector. The vector exists on its own. Okay. So, it is our description that brings in these indices. Now, when you have this notion, then it is easier to see as to why one can expect the diffusivity to be a second rank tensor, right. So, for example, let us go back and see what it is. So, let me say that the j vector is nothing but j1, j2, j3. So, I am living in 3-dimensional space, the flux is in the 3-dimensional space, so that is j1, j2, j3. Now, del c, which is composition gradient, which is nothing but dou c by dou x1, dou c by dou x2, dou c by dou x3. Right, composition gradient resolved along the 3 principal directions. So, sometimes, I mean, that is why del c is also, so like this is written as j I, sometimes del c is also written as del I c, where I basically represents whether, so del I is nothing but by dou x I, right. So, now you can see that I have j1, j2, j3 equal to minus d times dou c by dou x1, dou c by dou x2, dou c by dou x3. This is one of the relations that we can write, where basically what we are saying is that the first component is scaled by the same diffusivity and second component and third component. So, basically this is just a scalar multiplying this vector. So, the flux vector is nothing but a scaled version of the composition gradient vector. This is what we are saying when we are writing it like this. But if you think in terms of matrix operation, for example, there is one more matrix operation possible, that this could be a 3 by 3 matrix, right. It need not be just a constant, it can be a 3 by 3 matrix. What does that 3 by 3 matrix do? Then the 3 by 3 matrix means that the flux along the one direction is dependent on concentration gradient in all directions. So is the flux along 2 directions, so is the flux along 3 directions. In this case, we will later show that this under certain conditions you can assume this D to be a scalar, but the most generic expression that I can write in terms of tensors, in terms of matrix notation is as follows. So, I say J1, J2, J3 is equal to minus D11, D12, D13, D21, D22, D23, D31, D32, D33, and then we say okay, let us dou C by dou x1, dou C by dou x2, dou C by dou x3, right. So, now you can see that D is a quantity with two indices. So, by our definition this will become a second rank tensor. Okay. So, now there is another way of writing this expression in a simplified manner, and that is by using what is known as Einstein summation convention. Notice that there are three equations here. J1 is equal to minus D11 dou C1 plus D12 dou C dou x2 plus D13 dou C by dou x3. That is first equation. J2 equal to D21 dou C x1, D22 dou C x2, D23. Sorry. The third equation is J3 is equal to D31 dou C by dou x1 plus D32 dou C by dou x2 plus D33 dou C by dou x3. So, even though this is written like this, there are actually three equations. Okay? And so, Einstein summation convention says that J of I is equal to D of I comma j del j c, okay, where del j c is my shorthand notation for saying dou c by dou x j. Okay, so this is a vector component, this is a vector component, and this is a second rank tensor. In the tensorial notation, when I do not refer to any specific frame of reference, they are written like this: J is equal to D, I draw two lines to say that it is a second rank tensor, del C. So, this one line says that this is the first rank tensor. So, J is equal to D times. So, sometimes in books this is written as a bold D, or sometimes it is written in handwritten things like with a double mark to say that this is a vectorial or tensorial quantity. Okay. So, the easiest is to draw lines. I mean, sometimes you keep on drawing as many lines as the rank of the tensor. The third rank tensor will have 3 lines below, and fourth rank tensor will have 4 lines below, and so on and so forth. So, it may be too many lines, but this is just to indicate that when I am writing in this fashion, I am not referring to any frame of reference. When I write in this way, I am referring to a frame of reference. In any case, vectors are quantities with one index, tensors, second rank tensors are quantities with 2 index, and so on and so forth. Now, what does the Einstein summation convention mean? Einstein summation convention says that the repeated indices are summed. That is, when you have j here in a term, that means there is a summation over j that is going on here, right? Because when you write this, you will see 3 terms summed up, okay, that we are not writing. And the free indices on both sides should match. If you have I free, it is not summed, then you should have one I here, because this is a vector. When you have one I, then the right hand side should be a vector. Suppose if you have I here, and if you do not have I here, that means you are equating a vector to a scalar. Or if you have I here, and on this side if you have I and k, then that means that you are equating a first rank tensor to a second rank tensor. So, which is obviously not possible. So, the total number of free indices on any term, it could be more than one term. In all terms, if you have I here, then every term should have one I which is not summed. This is important because then only you will have vectors getting added to vectors, otherwise you will be adding scalars or tensors to vectors. So, it is always a good idea, like you always check dimensions of quantities in an equation when you write this type of expressions, to see that the free indices match and any repeated indices are summed, and the summed indices are basically dummy. Okay. The j is a dummy. It is like, if I am integrating, it does not matter what the integration variable is. So, j I for example is equal to d I k del k c is the same as d I alpha del alpha c, which is the same as d I j del j c. So, the k, alpha, j, everything, I mean repeated index is basically a dummy index, because at the end of this exercise that index is not going to survive, that is going to be out of the calculation. So, you can use any index you want. So, this is known as a dummy index. And you need to make sure that in an expression you do not have more than one dummy index. So, that is also very important. So, for example, I can't write it as d k k del k of c, there is a problem, right, because k will be taking 1, then 1 1 it will always be, 1 2 will never appear, that is a problem. On top of it, if you have more than once the same index repeated, twice repeated, I know that it has to be summed. If it is thrice repeated, then what needs to be done, that is not clear. So, this is wrong. It should always be the repeated indices which are summed should appear exactly twice in any expression. Okay. So, this is all related to Einstein summation convention. Basically, Einstein summation convention makes the process of writing these complicated expressions very easy. We will see some examples later. Already you can see that 3 equations are being written with just one expression, right. So, I say j I is d I k del k c is basically equivalent to 3 equations in 3 dimensions. If I is running from 1 to 3, that is 3 equations. If I is running from 1 to n, it is n equations. Okay. So, already it is making everything very compact, and unlike matrix notation, you do not have to expand. You write this, you understand that this is what it is. Okay. Now, that naturally brings us to the question that if vectors and tensors are quantities which have a life of their own, they do not depend on how you describe them. But this definition that we used, namely in terms of indices referring to the rank of a tensor, requires us to indicate what the frame of reference is. So, how do we get rid of this dependence on the frame of reference in the description of tensorial quantities, because tensorial quantities live by their own, right. There is a concentration gradient or there is an atomic flux, that is irrespective of where you are going to fix your frame of reference. So, you can naturally demand that the way we describe, I mean I might use a frame of reference and some of you might use some other frame of reference, that should not affect the way we describe these quantities, because these quantities have a life of their own. Whether I choose this frame of reference, you choose that frame of reference, does not matter to the flux. Flux is going to be in a particular fashion. Okay. So, it is very important that we try to get rid of this dependence of the indices on the frame of reference that we choose by trying to see what is the effect of changing a frame of reference. Suppose I do with one frame of reference, you do with some other frame of reference. If we can come to a conclusion as to what is the effect of this change of frame of reference on these quantities, then we would have defined the tensors as quantities which have a natural existence of their own, without reference to the way in which we describe them using frames of references. Okay. So, that is what we will do next in this lecture. Thank you.